Artie, for the introduction, and thanks for the invitation. So this talk is about model selection over partially ordered sets. And before I start, I'd like to acknowledge my collaborators, Peter Buhlmann at ETH Zurich and Venkat Chandrasekaran at Caltech. Okay, so at a very broad level, what this talk tries to address is the replicability crisis in science. And what this really means is, suppose I'm running some scientific study and I maybe analyze data, maybe I run some experiments and I come to a conclusion, and you're going to try to do the same. And our results, our conclusions could be potentially very, very different. So this mismatch that has happened, especially recently, has been widely reported in the literature, has created a lot of issues about, whether science can be trusted, and, really is raising the question of whether our studies are replicable. And there's many reasons for this. Reasons such as like the publishing culture that we have in our fields, the experimental reproducibility. Maybe it's very hard to kind of replicate an experiment because it consists of a lot of resources, as well as many other reasons. The one that I want to focus on for this talk is a statistical one, which is the lack of statistical confidence for scientific discoveries. And within that, what I want to focus on is the question of, can we control for false discoveries in our data analysis pipeline? So we are using data, we come up with discoveries, and we'd like to ensure that all of our discoveries, or most of our discoveries, or some large proportion of our discoveries are correct. And it's okay if we don't make many discoveries possibly, but we just want to be confident about the scientific discoveries that we're making. Okay, and if I'm sure many of you guys are familiar, there's a long literature, many areas trying to address this question. And the usual paradigm trying to address kind of controlling for false discoveries kind of goes as follows. You formulate and test a collection of Boolean hypotheses. So you ask questions like, is this edge present or not in a graph? Is this variable relevant or not for prediction? So you have these maybe collection of null hypotheses that you test. And then it's straightforward to assess, maybe I put straightforward in quotation, because sometimes it's maybe potentially difficult, but relatively straightforward to assess and control for false discoveries. So discoveries in general means attributes that you find. So this is like an edge being relevant, a variable being relevant. False discoveries would mean attributes incorrectly included. So you say that a particular gene is relevant for predicting a disease when it actually wasn't. And by now, there's many approaches to control for false discoveries. Okay, so the focus of this talk is what happens in non-Boolean settings, problems that lack Boolean logical structure. Somehow there's a lot more complicated structure underlying the problem. So as an example, in ranking, there is a global structure of transitivity that you need your models to satisfy. In clustering, there's a global structure of set partition structure that your models need to satisfy. In causal discovery, there's a global structure of acyclicity, blind surf separation. It's a continuous structure. In all of these problem settings, it's not immediate to think, can I use the previous formulations, the usual paradigm, to select models that control for false discoveries, because it's not naturally amenable to yes or no questions that we're used to asking. And I'll be more and more clear about this as I go through my talk. And what I would like to kind of get at quickly is what happens if I try to at least apply my usual paradigm, the one I'm really comfortable with, that I've seen a lot, in these non-Boolean settings. And I would like to convince you that there's two kind of shortcomings that happen, two major problems. The first one is that you could get invalid models that are inconsistent. And the second is that you may get a measure of false discoveries that doesn't seem natural, that doesn't seem to respect the underlying structure, complex structure that's in these problems. By the way, you can always ask questions if it feels like it's very serious. I think it's because I'm standing behind the podium, I feel. Okay, so the first one is invalid models. So let's consider a ranking problem. Ranking 3 items. And so I could have a collection of null hypotheses, which I denote by H0 down here. So I could ask, like, the null hypothesis is 1 is less than 2. I reject it, so I conclude that 1 is bigger than 2. I can ask the same question about 2 and 3 and 3 and 1. And so I get a bunch of rejections. Is there a problem with this model? I guess I write it here, that it violates transitivity, right? So I've rejected these pairwise hypotheses, just thinking like everything is going to be fine, but then ultimately I get a model out that doesn't actually make sense, that violates kind of a structure that you want from this problem. And this is not just for ranking. So for causal discovery, you think about, maybe I want to learn a directed acyclic graph. So this is a graph with directed edges and no cycles. So I could think of maybe possibly pairwise hypotheses between nodes in the graph. So maybe 3 nodes here, 1, 2, and 3. So I ask questions like, there's no edge from 1 to 2, 1 pointing to 2, or 2 pointing to 3, and 3 pointing to 1. And I could perform all these hypotheses, hypothesis tests. I reject, let's say, all of them. And then I could get a model like this that violates acyclicity. So it's outside of the model class that I'm actually looking for. And so this problem is not just a problem with ranking or causal. It's a problem with many modern complicated settings that we are interested in. So partial ranking is another example, clustering is another example, multi-sample testing, and many, many others. So that's the first one, invalid models, if you kind of take a usual perspective. The second one is about inaccurate measure of false discoveries. So let me take a clustering example, a very simple one, clustering 3 nodes, A, B, and C. And clustering, what you're interested in is grouping items based on affinity. So suppose there's a true cluster where A and B are clustered together in one group and C is by itself. And I estimate a cluster that is A, B, and C. So everything is together. Okay, so if I take the usual paradigm and think about, okay, how many false discoveries have I made? You would answer 2 because you would think, well, A and C are clustered together, and that's wrong because that's not in the truth. And B and C are clustered together, and that's wrong because that's not in the truth. So that's 2. So I count 2. Does anybody see what's wrong with this? Is there a better answer here or a more natural answer? He was in my class, so that's why he knows. But yes, the answer is it's wrong because a more natural answer here is 1, because you've already correctly put A and B together in your estimated model, and you just added C to it. So this second perspective takes into account the set partition structure that's underlying this problem. It doesn't think about, pairwise things like we're used to, whether this is correct, whether this is correct, but rather it takes into account the structure that's underlying this problem. Okay, so this example is not just, this problem is just not just with clustering, but also with causal discovery. So here the task is, yeah.
Is it fair to say that one is correct as opposed to like a more, because these are both like
yeah. So
so you're arguing that like this is a
more appropriate. Yeah. So yeah, in the next example, I will use more natural. I think I would always prefer saying more natural.
Okay.
Sorry about that, but yeah, because it's my take that this is correct.
Yeah, so depending on the setting, like we might actually care about dyadic
Could be.
fusion.
Could be.
But I agree that that's probably less accurate.
Yeah. Thank you. Yeah. More natural. Okay, the second setting I want to talk about is learning a CP DAG. So this is an equivalence class of DAGs. That's not so important for you to know. I'll talk about the things you need to know for this. So suppose I have a true CP DAG that's presented here, and I have an estimate that's presented here. The estimate has undirected edges because of identifiability issues. The edge could point in either direction. And so you can try to think about what's the number of false discoveries that you made with your estimate, given that that was the truth. And the Boolean logical perspective would say 2 because, well, I estimated maybe 2 edges here, right? And both of those edges don't seem like they're they're the same as the edges that's in the true model. Something seems incorrect here. Does anybody see what's maybe strange about this way of thinking? Okay, so I claim that a more natural answer is 0, because every conditional dependency relationship, sorry, that's supposed to be dependency, not independency, and that's a major typo. Sorry about that. Hopefully I don't make the same mistake elsewhere. Every conditional dependency relationship in C hat is also in the true model, okay? In some sense, your estimate is kind of a submodel of the true model. So the perspective here I'm taking is that if I declare an empty CP DAG, I'm declaring no causal relationships. I'm just saying nothing about my set of nodes. I don't know anything about any variables being causally related to another. Here in my estimate, I am declaring some conditional dependency relationships, some causal relations, and every dependence relationship that's encoded in this estimate is also in the true. It just means that the edge could go in that way or in the other way. You're not speculating because you can't. From the observational data, you don't. Andres. So this is a conversation I've had before. The perspective here is different than the perspective of maybe what perhaps you're used to about empty DAG encoding a lot of assumptions. Here, the perspective I'm taking is I want to maybe tell a scientist or a practitioner, here's maybe a collection of genes, and I want to find out which ones are maybe parents of a particular response variable, like which genes are causally predictive of. No, so it's not about assumptions. It's not about what I'm claiming here is not about assumptions, whether one has a weaker assumption, or it's more about we don't know anything. So the setting is that the empty graph is no knowledge. Just like in variable selection, if I output an empty set of variables, I'm just claiming that I don't know any variables being predictive of my response variable. Here, an empty graph, the way I'm viewing it is that I don't know any causal relationships. I'm not telling you as a practitioner that these two things are related to one another. So there's like I was told that this is akin to causal null effect, that's my null, that these two variables are not causally related. And so think of it as a treatment effect type of thing. I have a treatment. My null is that the treatment has no effect. So there is no connection between the treatment and the right. And I'm wanting to declare to you, I'm rejecting it, and there's a discovery, so there is an edge. So that's the perspective I'm taking here, because that's very similar to the multiple testing perspective. Hopefully that answers. It's a philosophical question that it takes, I think, a conversation to describe. Yeah.
And it's like, I don't need to pull it because a typo, but so I understand like a conditional independence relationship is.
Yeah.
But dependence is independence is a special type of dependence, right? In a strict sense. And so what does it mean for every conditional dependence relationship? Like, so if I correct that and say every conditional dependence relationship. So
X1 and X3 are dependent on each other. X1 and X3 are so in the estimate, X1 and X3 are dependent conditional on any set of variables in this graph. That's what that means. And then this is also the case in this graph to the left.
Isn't it, I mean, I guess you mean like non-trivial dependence?
Yeah, non-trivial. Yeah, non-trivial dependence, non-zero. Yeah. Just think of it as like your regression, this thing is non-zero versus zero.
Yeah, because you're saying dependence.
Yeah. So usually you think of a null hypothesis as the regression coefficient being 0 versus non-zero. 0 here is that there is
non-trivial dependence.
Yeah, exactly. Any other questions? Okay, so you could argue, well, maybe that's not, maybe I can make the usual paradigm work because I could say, well, oops, in my estimated CP DAG, there is a particular DAG that has all the edges in the correct direction. So the number of false discoveries is 0. I can make it seem like it's 0. And that's true for this problem. But then I could come up with another setting where I kept the truth the same, but the estimate now is different. It's another CP DAG. And now you look at the two and you'd be like, well, there is, all the edges seem to point in different directions. So I'm going to claim that there's 4 false discoveries here. So I have 4 edges in my estimate. All of them are incorrect. And again, that's a bit weird because these two graphs share a lot of similarities. There's a lot of conditional dependency relationships. That's the same in the left one. That's also in the right one. And so what I think is a more natural perspective is to think about it as follows, where you think there is this common model that's shown to the right here. And what's special about this common model, every conditional dependency in this model is also in the estimate. So you think of it as like a subcomponent of your estimated model. And what's also special about this is that every conditional dependence here is also in the truth. So if I'm starting from an empty graph and I get to this model here, I haven't made any false discoveries. Everything I've added so far is good. But the mistakes I've made is going from this model to this estimated model. Those 2 extra edges that I added were incorrect because now the conditional dependency relationships that are encoded after I add those edges are not in the truth. So then I think a more natural perspective is to think that there's 2 false discoveries here. Okay, and so this shortcoming of an inaccurate measure of false discoveries, it's not only a problem with discrete settings, but also in continuous settings where it's clear that it's just a discrete way of thinking about things is not natural. So some continuous problems, for example, are subspace selection. You're estimating a subspace, or blind source separation where you're estimating source vectors. And maybe the usual Boolean logical perspective would say false discoveries would be something about exclusion of a true subspace or a true set of vectors. And if you think a little bit about this, this seems very wrong because you would generally declare everything to be false discoveries because of the continuous nature of these problems. And a more natural perspective is a degree of alignment between true subspaces and vectors. And this was already kind of addressed in my previous work, but it's still, there's a lot of open questions there. But just saying that there's this issue is broad in discrete settings as well as continuous settings. Okay, so I already covered these 2 major shortcomings. There's a need for a new perspective that accounts for complex structures, and that's what I would like to address. And so the idea, what I'm proposing, is to organize the models according to a partially ordered set, so a poset, and that leads to a hierarchical organization of models. So what posets do is that they are somehow complex enough to encode all the complicated structures that we've talked about in all these model settings, but somehow structured enough where they lead to a framework, a unifying framework to measure true and false discoveries that addresses the challenges that we talked about earlier, and efficient approaches to control for false discoveries. So my world somehow has become posets in the time that I've worked on this project, and I would like to also share that perspective with you, and hopefully you can see the same way as me. Okay, so let's talk about model organization over posets. So what is a poset? It consists of 2 things, a set of elements, L, and relations. So the relations need to satisfy reflexivity, transitivity, anti-symmetry. I'm just saying this just so to be complete. It's not relevant for the talk, but it needs to satisfy some properties. But let me give you an example of what a poset in variable selection would be. So this is a variable selection where you have 3 variables. And the set of elements here, L, is the power set of A, B, and C. Right? So you have the empty set, you have each of these by themselves and then together and then the full set. And the relation here is subset inclusion. So here C is bigger than the empty set because the empty set is contained in C, or A and C is bigger than C because A and C, or C is contained in A and C. And this diagram, it's known as a Hasse diagram. It encodes the ordering if you look at the edges. So the directions kind of tell you how things are ordered. And it's a partial order because not everything is comparable, right? So I can't compare A, B, and A and C. They're incomparable. So that's where the partial order comes from. So the way to think about L and the containment or the ordering thing is think of it as a space of models. So every element in L is a model. And the ordering tells me about containment between simpler and more complicated models, right? So the empty set is the least complex model. And then you get more and more complicated model, and the ordering kind of tells you the containment between simpler and more complex. Yeah. Go.
So formally, should I think of the domain of the relief function as simply not being like the Cartesian product of L with itself? Or should I think of the codomain of the relation having like three results, which is like A is less than B, B is less than A, or undefined? Or is that just a matter of like mathematical convenience?
I think it's a matter of mathematical convenience. Think of it as I'm a little bit uncomfortable.
It's like a group then.
So think of it as it takes two. So it does take two elements, or you take any two elements in the post set and you try to relate them.
But it can return as a result of like no work.
It can return not. Yeah. It can return nothing.
Okay.
Yeah. Good. Okay, so now let's think about, before I talk about another application, there's a couple of attributes that are really important about post sets that will show up over and over again in my talk. The first one is a least element, so that's the smallest element in the post set. And think of this as here, of course, in the variable selection setting as the empty set. Everything is bigger than this. The other one is the rank function, which is there's a very formal definition for this from order theory, but the way to think about it is the number of steps away from the least element, right? So the rank of this thing here, A and C, is 2 because it's 2 steps away from the least element. The rank of these things is all 1, and the rank of this thing is 3. And of course, in the variable selection case, it's set cardinality. Yeah. Just set cardinality. Yeah. And really, the way to think about the least element is just the global null. You know nothing. Your current status, your current state, you make no discoveries. And the rank function tells you something about the model complexity, how complicated the model is. Okay, let's get more complicated. So here's now the post set for clustering. So you're grouping items based on affinity. The space of models, the set of elements, I think of this as the partitions of a set of P items. So here, what I've drawn is a post set of four items. So the bottom is every item is in its own group. So I think of this as no discoveries, that you just have not grouped anything together. And at the top, I think of it as you put everything together. You've discovered a lot. So the ordering in this post set structure is refinement of a partition. So what I mean by that is, so this item here is bigger, or this element is bigger than this element, because this is a refinement of what I have here, right? So the ordering is based on the refinement of the partitions. The least element, I just said, everything is in its own group, and the rank function, mathematically here would just be the P minus the number of groups. So this would have rank equal to 0. This would all of the elements here would have rank equal to 1, rank 2, rank 3. Yeah. Great question. No, post sets, that's not, so post sets also don't need to have a rank function. It's a graded post set that has a rank. I just didn't want to introduce all these words. Also, post set doesn't need to have a least element, but every post set I talk about in this paper and this talk has a least element. It's an interesting question whether whether what I talk about can be extended to settings where there's no least element. Yeah. You could think of it as the opposite direction. Yeah, so I've heard this comment. So I think of I think of the other direction as we call it multi-sample testing. It's a little bit matter of taste, and I would like to talk to you about that. Okay, sorry. Well, yeah, so sorry, maybe that was a bad comment. I think I just mean the other direction is totally possible. And so it's actually another example in our problem setting. Yeah, it's I think good to talk about this offline. Yeah. Somehow I think if you have a collection of items and you don't group anything together, then the state of no knowledge seems to me that you don't know anything, so you just put every item in its own group. That's how I think about it. But you can reverse this poset. It's symmetric. Still works, yeah. I call that problem something else, multi-sample testing. Yeah. And in fact, maybe I'll talk about the causal one. You can reverse the causal one and maybe you'll be happier too. And I think both are fine. I think some would say the one I have in, well, at least me and my co-authors think the one I have here for clustering can make sense. The one that we have for causal can make sense, but the reverse can also make sense depending on what you're interested in. Yeah, for your application. Yeah,
This is giving us a formal framework.
Yeah, exactly. Okay, so here we go to the causal one. So the space of the set of elements here are CP DAGs on set of 3 variables. So here I have 3 nodes and I drew all the possible CP DAGs. So it's a poset. The ordering is based on inclusion of conditional dependence relationships. So I didn't make a mistake here. So, this graph here is bigger than this because every conditional dependence here is also encoded here. And you can kind of go up the poset structure here. The least element, the global null, is the CP DAG with no edges. So no causal relations between the variables. And the rank function is the number of edges in the CP DAG. So this is 0, 1, 2, 3. You could reverse this and just have to modify the rank function. The least element would, of course, now be this, but yeah. The poset structure more or less is similar. So, and you also have inclusion of conditional dependence relationships would be inclusion of conditional independence relationships. And more or less most things I say will go through. Good. Yeah. It's a CP DAG. So you can, there's many possible DAGs here. That's why it's all. So you can put this edge here, and then this edge the other direction. So that there's many possible orientations of the edges. And so that's why it's a complete graph. It's not a DAG, it's a CP DAG. Good. The other application I want to talk about is partial ranking. So you're ranking a set of items, and you're allowing for comparability. So you're saying that some things are incomparable to other things. The space of models here are relations. Again, sorry, I have to be mathematically formal, but the relations need to satisfy a few things: reflexive, asymmetric, and transitive. It's a poset on posets. Yeah, perfect. Yeah. So an element here, for example, so here the empty set, meaning that there is no relation between the items. So I'm not declaring one being bigger than the other. Here, for example, for this model, what I'm saying is A is bigger than B. For this one, what this means is B is bigger than A, and so on. And then here, what I mean here is A is bigger than B and C is bigger than B. There is a natural ordering, and that's based on set inclusion. Notice that this kind of structure is a bit complicated where there's a lot of elements at the top. There's not a unique element at the top, which is unusual given the other applications, but this kind of shows the complexity of different poset structures and how rich the model spaces can be. And all of that somehow still falls under the same poset framework. The least element is the empty set, and the rank function is the set cardinality here. So the cardinality of every element. So rank 1, rank 2, rank 3. Any questions before I? Yeah.
So is the rank always going to be like a kind of trivial thing to compute? You can compute just by looking at elements, or do you sometimes have to like resort essentially like counting the shortest path? Or are all the examples you're using? I mean, I guess it's always computable.
So a rank function is something you define.
Yeah.
So you.
But it has to coincide with the distance.
Right? Yeah. It always has to coincide with the distance. Yeah.
And in these are different cases where the rank is very.
Is very convenient. Yeah, yeah. There are settings where the rank is not. Yeah. There are settings where I can't find a rank, actually. It's not graded.
If I define my relation in a very literal functional sense, there's no logic, but I just say like triangle before square.
Yeah.
Right. The rank then would just require use of like walk the graph.
Yeah. Right. 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 Okay. So posets are everywhere if you get into my world. So total ranking is another example. Multi-sample testing, which is the reverse of what Daniela's question is, the other direction. We think of that as multi-sample testing, where you say that this distribution of all your items are the same, and then now you would want to test against that. So that's the global null in that setting. Multivariate change point detection falls under this. Subspace selection, which is a continuous problem, falls into this. Blind source separation, which is another continuous problem, falls into this. So it's a rich framework that encompasses many complicated structures, both discrete and continuous. Okay, so now I will move on to false discovery control over posets. Any questions before I do that? Okay, so I have an element, I have an estimate, x hat, and I have a truth that's shown in green. And the question is, how do I quantify true discoveries and maybe subsequently false discoveries? So I have this poset, I have these estimates. I have an estimate and I have a truth. You guys have a guess of what's natural here? A natural way to define, let's say, true discoveries, like how much of x hat is in the truth? Well, right now I'm just saying, suppose I get an estimate x hat and there's a true. How do I even measure true discoveries? Intersection. What does intersection mean? In this case, what would it mean? I mean, here, I haven't even defined this. I haven't defined it, like what x hat and x star is, but just graphically here, like, can you, what, 2? You're saying it's 2? Why 2? True discoveries. I want to know what true discoveries would be. Yeah. Yeah. Perfect. Why is it one true discovery? Yeah, perfect. Yeah. So the way to think about this is, or I'm maybe trying to set it up for what's going to come in a few slides. What Keshav nicely said is there is this model right here that's less than both of them. That's the biggest model, the most complex model that's less than the truth and the estimate. And this model has complexity 1. And so that kind of naturally represents the amount of true discoveries you've made. Right. And false discoveries would also be 1 because then you subtract the complexity of your estimate, x hat, which is 2, and you subtract 1 from it, so you get 1. Yeah.
Is it fair to say that this is going to be like the distance to the nearest common ancestor?
Basically, exactly. Yeah, perfect. Yeah. I'll get there. But before I get there, so that's a very natural notion, but I want to be precise a little bit about how you measure similarity between posted elements, because what we just described is one way to measure it, but doesn't need to be always that case. So here's kind of a similarity function. There's a lot of notation here, but I will go through in words what it means. So the similarity function, what it takes is two elements in the poset and gives you some measure of similarity. Ultimately, that's what's going to be used to define number of true discoveries. So to go through the setup, let's think of X as my estimated model and Y as my true model. And so rho of XY is always going to be my size of true discoveries. So now let's think about what these definitions mean. So the first one says that my size of true discoveries is always above 0 and less than the complexity of the true and the estimated model, which seems very natural because your size of true discoveries shouldn't exceed either complexity of your truth or your estimated model. The second one says that more complex models means more true discoveries. That also feels like it's natural. If I'm strictly increasing in complexity, then I'm making more, at least the same amount or even more true discoveries. Higher up. In the CPDAG world, or flip it around,
It's greater rank.
Greater rank, yeah. Yeah. Yes, exactly. And the last one is that the size of true discoveries is equal to the complexity of the estimated model if and only if the estimated model is contained in the true model. And that again feels like a natural property to have. So I'm saying that this is something we call this similarity evaluation because in order theory, that's what people call a function that takes two elements in a poset and returns something. We've defined these notions of 1, 2, and 3 for specific to the problem of model selection and multiple testing, because we think these are somehow axioms that you need to have satisfied. We don't necessarily, there's natural row functions to take, but at least they need to satisfy all of these three properties, we think. So once we have a similarity evaluation function, rho, here is what formally are notions of true discoveries, false discoveries, and false discovery proportion. So true discoveries would take the similarity evaluation and plug in your estimate and the truth. False discoveries would be the rank of the complexity of your estimate minus the number of true discoveries, and false discovery proportion would be number of false discoveries divided by the complexity of your estimates. Right. You plug in you take in the row function that a lot of you guys guessed, and you plug in the variable selection poset, you get what you're very much used to. Okay. And so the natural goal for model selection is identify the largest rank model subject to control over false discoveries. And that could be an expectation or a probability of making any false discovery or proportion of false discoveries, but large rank model subject to some sort of false discovery control. Is the goal clear? The motivation? Yeah. Okay. So we've already talked about what is a natural notion, which is based on meat, a concept in order theory, which is exactly what you guys said. Take the largest rank model that's less than your estimate and your truth. And the rank of it would be the complexity. Now, the largest rank model is actually not unique, doesn't necessarily need to be unique. In some settings, it's not unique, like the causal world, but we're just taking the rank of it, and that's always gonna give you one value, so that there's no issue with uniqueness there. So true discoveries, if you take this row function, it's just the complexity of the largest complexity model that's contained in your estimate and in your truth. And false discoveries would be the complexity of the estimate minus the number of true discoveries. That's how you can say what true discoveries and false discoveries mean in words if you plug in this row function. Is that clear? Yeah.
So just clarifying question, you've drawn the posets right before
Yeah.
the edges.
Yeah.
Right. You haven't actually been drawing all, like, an edge is not actually equal to a valid relation, but like a path is instead a valid relation.
Yeah.
Right? Because like, for example, the least element.
A path is a least element. Yeah.
Right? Because like there's still a well-defined relation between like rank 3 and least common element.
It's a path, yeah. It doesn't necessarily be, they're not directly connected, but there needs to be a path.
Yeah, but like at least in the definition of the ordering,
yeah.
Like C allows you to go multiple steps.
Multiple steps. Yeah, in the example, we only went one step, but you could go multiple steps. Yeah. Any other questions? All good? Okay. So let's talk about what this notion means. We already talked a little bit about it in variable selection. If that's my estimate and that's my truth, the shared model is here. So then the complexity of this is 1 and the false discoveries is 1. So it kind of checks with the notion we're used to, which is the number of selected variables that's not in the true model. And the model selection goal is the usual goal of maximizing the number of variables subject to some control on false discoveries. Let's talk about clustering, and Daniela may be unhappy with this, but reverse it always. So suppose this is my estimate. Everything is clustered together. The true is here. Row meet. I haven't drawn the yellow because you know where the yellow is, which is the common between the X hat and X star. It's the green itself. And so this evaluates to 1 because the complexity of this thing is 1, and the false discoveries is also 1 because the complexity of this is 2. So 2 minus 1 is 1. And in words, what false discoveries would mean is the number of groups in the coarsest common refinement minus the number of groups in X hat. You could reverse this if you want to think about the reverse poset, and I'm happy to talk about this too offline. What this really means is how many steps is your truth away, or how much your truth is away from being a refinement of your, how much your estimate is away from being the refinement of your true model. That's what false discoveries would count. And the model selection goal was to minimize the number of estimated groups subject to control on false discoveries. Okay. And so if you want to think about the reverse one, instead of coarsest, use the most refined, and then common refinement will be the common coarsening. So everything can be flipped. Okay, here's the causal one. Here's the truth. Here's an estimate. They happen to have this unique, similar kind of intersection that's shown in yellow. And so the row meet here is 1 because the complexity of this thing is 1, and false discoveries would also be 1 because this is the complexity of the estimate is 2, so 2 minus 1 is 1. And if you try to say what false discoveries would mean in words, what it is the number of edges in your estimate minus the number of edges in the densest CP DAG that contains all the conditional dependencies encoded in both your truth and in your estimate. So another way to think about it is how much is your estimate away from encoding all the conditional dependencies that's in the truth? Or sorry, how much your estimate is away from a model whose conditional dependencies are all encoded in the truth. Right? You can always flip this around and say, how much is your model away from including a model that contains all the conditional independencies that's also in the truth? Hopefully, there's a lot of words I said, but hopefully you guys are getting the, because I'm trying to cover all possible ups and downs of this, but hopefully it makes sense. Ask me questions if it does. Okay, and the model selection goal is clear. Go up here, meaning maximize the number of edges in your CP DAG estimate subject to control on false discoveries. Okay, it's important for me to talk about this because we talked about a notion of row. It depends on the application. It depends on the expert. There are settings where it's actually not natural to use row meet if you think about it carefully. Like in total ranking, if you think a little bit, it's more natural to use intersection of inversion sets. I don't want to get into talking about inversion sets, but it's an object that comes up in ranking, and that's a lot more natural to use here. For anything continuous, you cannot use row meet because intersection is always empty. and a subspace estimate and the true will usually have a zero intersection, no commonality. And so you have to think about some other measure. And so we already did that in a previous paper, but it's also written in this paper. So it's important to say that the utility of inference critically depends on a well-chosen row function, and that's similar to using a good loss function in estimation. So it depends on what you'd like to use here.
If you don't have a least element, right, if your set's not bounded below, then row mean isn't even guaranteed to be defined everywhere, right?
Yeah, that's right. That's right. Yeah. Well, row mean is always no. So even if you have multiple minimal things, row mean will just give you zero because it just cares about the rank. It doesn't care about that there exists a unique z that's less than your estimate and the truth. It just cares about the rank of it. So row mean is always well defined, even if there is no unique minimal elements.
Well, so I'm considering.
But let's talk about this offline because I think so I want to get to the algorithms because I think it's important to get there soon. So here is the way to think about developing algorithms and a useful way of going about it. So if you think about my model being here, x hat, and the true being here, x star, think about a path from my least element to x hat, right? So I take this path. Then the amount of false discoveries I make can be written as a telescoping sum, as this particular telescoping sum, where every term here can be viewed as the additional false discovery incurred by model xi relative to model xi minus 1. So as I go from here to here, how much false discovery I make is exactly, you view it as this. And then from here to here, it's another sum, and I just keep counting. Okay, so this is a path from x0 all the way to my estimate, and then I have a telescoping sum decomposition. And for the purposes of this talk, I will always refer to this pair of elements, xi minus 1 and xi, as neighboring models. So they are, one contains the other, and their complexity is different by 1. So xi is bigger than xi minus 1. So the model in xi minus 1 is contained in xi. And for all of such pairs, we want this object to be small. So 1 minus the difference of the row functions, because it appears here, to be small. Because if this is small, then this is small. Perfect. Always gives you the same value. It's always the same value. I could have taken any path. Yeah, I wanted to say that, but I didn't. But thanks for asking it. Yeah. It's useful to think about a path to just come up with an algorithm, but it doesn't matter. For any other questions? Okay. So this suggests a very natural, what I call an oracle greedy algorithm. So you greedily grow the model. You first need to specify a user parameter, call alpha. So alpha, think of it as being very, very small. You start from the least element and you find a neighbor v. So the least element I call u. Then I go to v, that's one more complex than u, and I check to see, and I try to find the v that minimizes this, because this was the amount of false discoveries that's in v and not in u. So that's in v and not in u. So the amount of new false discoveries that I incur. So I want to minimize this, and I want it to maybe be smaller than alpha, much smaller than alpha. And if I can find such a v, I go to that v and I repeat this process. Is that clear? So in this, I look at every path here, every one step here, and I check whether I try to find the one that minimizes this quantity in the first step. And I go to that one if it's sufficiently small, because if all of them are large, maybe I shouldn't go to any of them. If it's sufficiently small, then I go to, let's say, this model, and then I, again, check all of its neighboring models. When the alpha thing cannot be met. So alpha, think of it as like 0.05 or something like that. And at some point, you're not going to find a model that satisfies this. Is that clear? You will stop. I mean, yeah. You will stop. This is, you can apply this for continuous settings. This is exactly actually an algorithm that I had a couple of years ago. You can think of it in the discrete world. But you have to think about things in the right way, but it's similar. Okay, so the problem is that, of course, the truth is not known. And so you need a data-dependent version of this. I don't have access to X star, so I need to somehow think of what this quantity is, come up with a data-dependent version of this quantity. And I call this data-dependent function psi, and I'll describe examples of what it could be in a second. And so what criteria we need for this data-dependent function is that if this is small, this quantity is also small. Because we wanted this to be minimized, right, for every neighboring models. And so a useful data-dependent function would say, if this is small, so is this. And so there is many examples of it, or there's at least a few examples of two designs that we have for the function psi. So one is based on subsampling and stability. The other is based on testing. I think for now, I'm just only going to cover stability because of time issues. But I do want to mention a very important object here, which is a set S. And it's a minimal set of neighboring model pairs that characterize how much false discovery is incurred by any true model. It really captures all the invariances that exist in posets. There's a ton of invariances in the poset structure. So in fact, if you think about the number of neighboring models in variable selection, it's exponential in the number of variables. But if you think about the set S, what it actually is, its cardinality is P, because there's really P degrees of freedom. You don't need 2 to the P possible degrees of freedom here. And so the set S captures it. It's a combinatorial object that plays a huge role in our analysis and our algorithms, and it underpins the statistical guarantees that we have, as well as the computational performances. So here is the stability-based algorithm, and it goes as follows. I take my data, I subsample, and I apply my base procedure. So I have a base procedure, think of it as like k-means for clustering. I subsample my data, and then I repeatedly apply k-means, and I get a bunch of estimates. So I denote these estimates by x hat. Then there's an aggregation process, aggregation step after I got all my estimates. So for any pair of neighboring models U and V, I define my psi stable to be this object. So this looks a lot like the one that I had before, where x hat is now replaced. It was x star here and not x hat, because we don't have access to x star. So we just replaced it with an x hat and took an average. So what this really says is that if psi stable UV is small, that means additional discovery that's in V and not in U is supported by by a large fraction of your data. That it's very stable, that you can see this discovery over and over and over again in your subsamples. So maybe you're confident that this is a good discovery that you made. Is that clear? So, yeah.
And so I just took the higher goal to say we have a bunch of X hats and we're trying to find a final X hat.
Yeah, that's exactly. Yeah, we're trying to use some sort of commonality between all of them, some sort of stability that's common in all of them. Yeah. So you do this. The nice thing about if you think about this algorithm, and you specialize it to different settings, like variable selection, you get an existing algorithm called stability selection by Meinshausen and Blumen. If you specialize it to subspace selection, which is a bit Andrea's question, you get what I had in a previous paper, what I called subspace stability selection. So what our algorithm is useful for, of course, specializing into previous settings is nice, but it allows for a lot more possibilities. So it includes ranking now, clustering, and causal discovery, as well as many others. So you can apply this algorithm. Very quickly, I'll just talk about the theory. At a high level, what you're wanting to say is, I would want my false discoveries to kind of be equally likely to be contained in my estimate. And if I have that assumption, then by averaging, I'm just going to kill off false discoveries. And that's really assumption one, and it could be formally mathematized. The second assumption says something about your estimator being just better than random guessing, which here means normalized true discoveries better than normalized false discoveries. Under these assumptions, you conclude that any discovery that is false will be unstable when you compute this function. So stable things cannot be false discoveries or are unlikely to be false discoveries. And that comes from these two assumptions. And so you get a theoretical statement that I have here. What's nice about this, and I'll go directly to a few remarks about it. One is that if you specialize it to variable selection, you get a previously known bound, which is good, always specialize to existing things. The other is that everything here is computable in this bound. So Q and S, so S was the minimal covering pairs, and SK is a restriction to a particular rank. You refer to my paper because it takes some explaining here, and I don't have the explanations because it requires notation. But the point I want to make is that everything is computable, and some of the things here can be adjusted by the user. So alpha is a threshold that we get to choose, and this Q, think of it as a tuning parameter, let's say in the Lasso, for example, or in any regularized estimator, or in the number of clusters you use in k-means. If you tune that, you get a different value of Q. So essentially, what you could do is reverse engineer. So you could tune your base procedure and look at the values of Q you get and compute this bound and use this bound to decide, okay, if I want 5 false discoveries, how much should I tune my base procedure so I can achieve this bound? Is that clear? So you can use this bound to then come up with the base procedure that you would use and ensure false discovery control. And I would just want to conclude, so I'll skip the testing. There's a natural testing thing to do. That if you apply the stability-based procedure, here's different problem settings like total ranking, clustering, and causal discovery. And for the base procedure, let's say for total ranking, I use a common thing, which is a Bradley-Terry-Luce model. You can tune it so that you can get different model complexities. Here, the blue is if you were to run the procedure normally, like you output what's normally done. So the x-axis is the size of false discoveries. The y-axis is the size of true discoveries. So that's the blue. Different problem instances are different points here. The green is a desired false discovery control that I set here to be 3. So I want my algorithm to produce at most 3 false discoveries. And so we run our algorithm based on the bound to achieve the bound of 3. And this is the result we get, all these points here that's shown in the red. So we have effectively achieved the desired goal of having fewer than 3 false discoveries. We've paid for a little bit of price and power, but at least we have the desired false discovery control. And the same thing we have for clustering, where we had a desired level at 3 here, and we achieve it. Here for causal discovery, again, we had a desired goal of 2 in this case, and we achieve it. Do I have any time anymore? Or I think that's good. Yeah. Happy to take any questions or some real data, but I think better to take questions. Thank you. Yeah. For this, yeah, you may get a, so yeah, you may get a different result. So in terms of like where the blue points are going to be somewhere else and the red points are going to be somewhere else, but you can still use the algorithm in the same way. You may have more power if you use a different algorithm, different base procedure. So the quality of the procedure in terms of power really is going to come in terms of the quality of your base estimator. So if you use a terrible base procedure, then the result of this is also not going to look very good in terms of power. You'll just make very little true discoveries. So it comes in that way. K-means that we use it because it's a natural thing to use for clustering. Yeah, Andres.
So it seems to me that spot point discovery are more costly than others. Some may be more dangerous, you may be missing some causal relationships that is more important than others.
Yeah. That's a great question, and I think maybe Daniela has worked on it a bit. At least I know one of her papers. So there is a notion of like cost associated with you can assign different costs to different false discoveries. So here I'm treating every false discovery as the same. They all have cost 1 or whatever. But you can, yes, you can think of it as a different cost and maybe a budget that you associate with different false discoveries. And that's a great, I don't know. I think that's a great thing to think about. I don't know. I'm a little, yeah, I don't want to comment on it, but I think it'd be a very nice thing to think about. Yeah.
Any other questions?
Yeah, Amy.
So what's the high level idea? Thinking it said, so you have a bunch of estimates, you might come up with the estimate that's the most probable. Is there what you're saying you have to be running into the sort of congruency of across your estimates as much as finding the largest estimate subject to some idea of discovery involved?
Sorry, it's a. Let me maybe repeat what it is, and maybe because I'm having a trouble understanding what your comment is. So the way I think about the way what this algorithm is doing is, okay, so let me back up. So there's this algorithm that just says I start from the smallest model and I build up my model. And I need to, every time I go greedily in this post set, I will check to see whether my data dependent function satisfies this alpha criteria. So I need to come up with this data dependent function. And the way I come up with the data dependent function is to say, I take a bunch of estimates from subsampling, and I will check whether the discovery that I make in every jump in the post set, like this psi UV that I have here, whether, oops. So this, what this says here is that I'm just checking to see whether the discovery that's corresponding to it from jump from U to V, whether that's represented in many of my estimates, in a large portion of my estimates. So that's what I meant to say here, that if this thing is very small, what that means is that the discovery that's encoded in V that's not in U, it shows up in a large fraction of my estimates. Like in 90% of my fraction of my estimates, this variable is important. This variable shows up in my estimates. The number of true discoveries is the common ancestor, the complexity of the common ancestor, because that's like the shared commonality between your estimate and the truth. And then false discoveries would be everything else. So like the from there, from the shared common ancestor, you took a jump to get to your estimate, so that extra jump would be a false discovery, for example. Yeah. Trees are data objects. So can you give me an example of? Okay. So each model, a model is a tree. Interesting.
We did, it was, we had it as an example, it's like a post set.
A post set of post sets? Yeah, you can think of a post set of a post sets. Yeah, yeah. That was a very special example. I'm not sure, quite possibly, but I need to think about it. I mean, one has to set it up carefully. Like it needs to, you need to think about an ordering. You need to think about a rank function, at least to use all the technology that I have here. Yeah, that's pretty cool. I'd be happy to chat more about this. Yeah, I don't know. It sounds similar to like the CPDAG world actually, because somehow the more natural comparison is that example, because every model there is a graph. As a side note, in the CPDAG world, some people, or in the DAG world, people think about partial order in the ordering of variables. That's the post set itself. What we have is more of a partial ordering in the space of models, which is somehow sounds more like what you'd want in your application, where every element is a model, which is a tree. Yeah.
Any other questions?
Yeah.
So quick one. So you had some table with the inside, I think the other one was side test. In general,
I skipped it.
How it decides. Like, I'm a little clueless, and I just do something wildly inappropriate. Like, do I suffer?
Well, you suffer from, theoretically, what you want out of the psi is this. So if your psi function, oops, sorry, what did I just do? You want this property to be true. Like if your psi function says that this between two models, this is small, you want also this to be small too, and this involves the truth. So if your psi, if you're completely clueless and you use a bad psi, then you should not trust your results, because this implication needs to kind of be true. Otherwise, the guarantees don't make sense.
So in general, I mean, you think carefully about whether they're my side too.
Yeah, so we have the stability one, which we can at least provide guarantees for, and the testing one, which I skipped. But those are at least two. But yeah, it's interesting to come up with more, and I don't exactly know what yet. But yeah, some thought is required. So this is a testing one, which is actually really interesting, but it's just a lot to cover. So I have to talk offline about it if people are interested. Any other questions?
If not, then let's thank
Thank you.
Erwin again.
Yeah.
Okay, thanks. My brain is